Ladies and gentlemen, welcome to Soar in Space. Today, I would like to discuss artificial general intelligence, AGI, not as a mythic endpoint, but as a possible system-level evolutionary process. Rather than asking, when will AGI arrive, I propose we ask, what does AGI actually mean? Where are we now? What is a plausible, engineerable trajectory toward it? And how might AGI integrate with the physical world? What is AGI? AGI does not have a universally accepted definition. However, within mainstream research discourse, it is typically described as a system capable of cross-domain generalization, continual learning, autonomous planning, and sustained task execution across diverse environments. The key distinction is not linguistic fluency, but domain general adaptive competence. In other words, current AI systems are highly capable at generating responses. AGI would require the capacity for structured, goal-directed, persistent action. 2. Where we currently stand. Most contemporary systems are built upon large-scale language models. These systems model statistical structure in language, capture broad declarative knowledge, perform pattern-based reasoning, generate coherent symbolic output. From a systems perspective, they primarily model declarative knowledge about the world. They excel at explanation, synthesis, interpretation, simulation of reasoning. However, sustained autonomous execution of complex, multi-stage objectives remains externally scaffolded. At present, there is no conclusive empirical evidence that scale alone, that is, parameter expansion and data scaling, is sufficient to guarantee the emergence of stable domain general autonomous intelligence. This does not rule it out, but it remains unproven. Third, a plausible engineering trajectory. Rather than framing AGI as a singular breakthrough, I propose an engineerable evolutionary hypothesis. A plausible trajectory toward general intelligence may involve the progressive integration of declarative and procedural structures. 1. Language model. Stage: systems learn declarative representations. They interpret and generate symbolic knowledge. 2. Tool-augmented stage. Models integrate with external tools, APIs, databases, execution engines, extending from symbolic generation toward operational capability. 3. Workflow structuring stage. Multi-step processes are formalized into structured pipelines. Tasks become repeatable, verifiable, and decomposable. 4. Skill formalization stage. Human expertise, including decision sequences, conditional branching, error correction strategies, and optimization patterns, is structurally encoded and modularized. Here, skills, workflows, or agents may be understood as one of the structural scaffolds through which intelligent systems transition from representational competence to actionable capability. This stage represents a movement from declarative knowledge to procedural knowledge. In cognitive science, this distinction is well established. 5. Skill model integration. If large volumes of structured procedural data are internalized, models may begin to learn not only what to say, but how to act. This suggests a future architecture in which language models handle interpretation and abstraction. Skill models encode structured action patterns. Hybrid systems coordinate both layers. This remains a hypothesis, but it is one with engineering tractability and theoretical coherence. AGI and cyber-physical integration. A critical question arises. If AGI remains confined to informational space, its impact will remain limited to symbolic domains. For AGI to produce sustained real-world transformation, it must integrate with sensor networks, actuator systems, feedback loops, control architectures. This is precisely the domain of cyber-physical systems and the Internet of Things. From a systems theory perspective, IoT provides perception and execution interfaces. AGI provides coordination, optimization, and high-level planning. Together, they form a closed-loop architecture: perception, modeling, decision, execution, feedback. The convergence of these layers could constitute a foundational transformation in infrastructure design. This alignment is not speculative fantasy. It is consistent with ongoing research in embodied AI and edge intelligence. Constraints and governance. Any movement towards systems with real-world execution authority introduces safety challenges, governance requirements, auditability concerns. As agency increases, so must transparency, constraint enforcement, verification mechanisms. Structured skill representation may therefore serve not only as a capability expansion mechanism, but also as a safety architecture foundation. Conclusion: AGI is unlikely to emerge as a sudden event. A more coherent interpretation is that it will be engineered through the gradual integration of declarative modeling, procedural structuring, tool augmentation, cyber-physical embedding. In this framework, skills, workflows, or agents are not endpoints. They are structural components in a broader architectural evolution. If AGI materializes, it will likely do so not as an isolated supermodel, but as a layered system embedded within real-world infrastructure. AGI, then, is not an apparition. It is an engineering project.